Hello everyone, welcome to the session on mechanics of materials, where we were discussing on module 1 the stress and strain. Till now we have seen lots of derivation, definitions and laws that are coming in first module, that is stress and strain. Today we will start solving the numerical problems in the module 1. So, before starting the numerical problems, I would like to list the formulas that we have derived in this particular module. If we start from the first session onward, we have started our discussion by explaining what are the types of stresses, what are the types of loads that are acting on a particular member or any component or any structure. So, the first fundamental definition we started is the stress. Stress is defined as the ratio of force by area, that sigma equals P by A. The unit of stress is Newton per millimeter square. Then we saw the strain. Strain is defined as a ratio of change in length to the original length or change in dimensions to the original dimensions, and it is a dimensionless quantity. Based on these two definitions and the law stated by Robert Hooke, we related stress and strain with the help of Hooke's law, that is, stress is directly proportional to strain within the elastic limit, and that proportionality constant is taken out by the modulus of elasticity E. Then we saw what is the elongation of a uniform cross section, what is the elongation of a stepped member, and what are the elongations for tapering sections, tapering bar with rectangular section and circular section. So, we know the change in length for a uniform cross section bar was given by delta L equals PL by AE. PL by AE, where P is the load, external load applied on the member, where L is the original length of the member, A cross sectional area of the structural member, E modulus of elasticity of the material from which the structure is made of. So, the extension of this expression was for tapering bar, where we solved for derived for rectangular cross section as well as for circular section. For rectangular section, it is delta L equals PL by TE into B1 minus B2 whole thing into log of B1 by B2, where B1 is the width at the larger section, B2 is the width at the smaller section. T is the uniform thickness of the rectangular bar, E Young's modulus of the material, P load acting on the member, L the length of the structural member which is considered. Then we derived an expression for change in length or elongation of the bar, elongation of circular tapering bar, where the expression was delta L equals 4PL divided by pi E D1 into D2, where D1 is the diameter at the larger section and D2 is the diameter at the smaller section. After these are the formulas, or these are the expressions that we have seen in our module 1. Based on these expressions, let us start solving the numerical problems that will be coming in this particular module. So, let us start with the first problem. The first problem goes like this. A circular bar, a circular rod of 20 mm diameter and length 500 mm is subjected to an tensile axial force of 45 kilonewton. Take the modulus of elasticity of a material as 200 kilonewton per millimeter square. 200 kilonewton per millimeter square. Determine the stress, strain and elongation of the bar. I will repeat the question once again. A circular rod of 20 mm diameter, length 500 mm is subjected to an axial tensile force of 45 kilonewton. Full stop. Take modulus of elasticity of the material as 200 kilonewton per mm square. Determine stress, strain and elongation of the bar. This is the question given to us. So, we should understand what are the given data in the problem. If we look into the first line of the problem, a circular rod of 20 mm diameter, it is a circular section. So, we will denote diameter with small letter d and the given value is 20 millimeters. The length of the rod is 500 mm. Length is denoted with capital L, L equals 500 mm. It is subjected to a tensile force of 45 kilonewton. Force is denoted with letter P. P equals 45 kilonewton. Then they have specified the material of the member, that is Young's modulus of a material is 200 kilonewton per millimeter square. 200 kilonewton per millimeter square. Though these are the given data in the problem. The first step in solving the problem is identifying the data given in the problem. After that, let us identify what are the unknowns to be found, what are the foundings that has to be done in this problem. So they have asked to find stress. We know the notation used for the stress is sigma. They have asked to determine the strain. They have asked to determine the elongation of the bar. So stress is sigma, strain epsilon, elongation denoted by delta L. So we have listed so many formulas coming in this particular module, and based on those formulas our duty is to determine these three unknowns, that is stress, strain and elongation of the bar. So let us start determining the stress. So the first one, stress sigma equals P by A. Unit of stress is Newton per mm square. Unit of stress is Newton per mm square. From the given data, we know the P, value of P is 45 kilonewton, but we do not know the cross sectional area. But they have specified the member is circular rod and they have given the diameter. Since we know the diameter and the cross section, we can find out the area. Area of a circular member is pi d square by 4. Pi d square by 4. Pi into 20 square divided by 4. So please calculate the value of A. So the value of A, pi d square by 4, pi into 20 square divided by 4. We get that value as 314.16 millimeter square. 314.16 millimeter square. So now we know the numerator, the load acting on the member 45 kilonewton. We know the denominator, that is area of the member as 314.16 millimeter square. Now let us substitute sigma equals 45 kilo, means it is 10 power 3 divided by the area 314.16. So solving this sigma, we get sigma as 143.24 Newton per mm square. 143.24 Newton per mm square. So we found the first unknown, that is stress. Let us go for the second one. Second one, they have asked us to determine the strain. They have asked us to determine the strain. We know strain is nothing but change in length by original length. So strain equals delta L by L, but delta L is not known to us. L, we know it as original length of the member, that is given to us as 500 mm. And in the problem they have specified a circular rod of diameter 20 mm. That means to say it is an uniform bar and the cross section will not change. So it is a uniform cross section. For uniform cross section, delta L is given by PL by AE. PL by AE. Let us find out that delta L. The delta L. Delta L is PL by AE. PL by AE. P, we know P as 45 into 10 power 3. The length of this member is 500 mm. The cross sectional area we found in the previous step 314.16. Young's modulus, they have given the Young's modulus as 200 kilonewton per mm square. 200 into kilo, that is 10 power 3. So on solving this, we should get the value of delta L. Delta L is 0.358 millimeters. So we found the change in length or the elongation. That is the third unknown which they have asked. Delta L, change in length or elongation. Now since we know the elongation and the original length of the member, this is the change in length and we know the original length. Can we find the strain? So strain epsilon equals delta L 0.358 divided by the original length. Original length is 500 mm. So if you solve this by using the calculator, we get it as 7.162 into 10 to the power of minus 4. Remember, as I said, strain is a dimensionless quantity. Strain is a dimensionless quantity. So we have determined stress, strain and change in length. Stress, strain and change in length. So these are the unknowns that were asked and we have found. So we have used all the basic formulas that we have quoted here: stress, strain and change in length. Now I will show you how to calculate the strain without using the expression of delta L. Without using the expression of delta L. We know some law. We know some law called as Hooke's law. The Hooke's law is stress is directly proportional to strain. We know stress is directly proportional to strain from Hooke's law. Hooke's law. And this happens well within the elastic limit. So we have sigma equals E into epsilon. E into epsilon. So our unknown is epsilon. Epsilon can be written as sigma by E. If you remember, we found the value of sigma. Sigma is 143.24. And if Young's modulus is given in the problem, 200 into 10 power 3. On solving this also, we get the value of strain as 7.162 into 10 power minus 4. 10 power minus 4. Now let us calculate the change in length again. So change in length, delta L, we know that strain is given by delta L by L. We know strain is given by delta L by L. Delta L is equal to epsilon into original length. So we have found out the strain 7.162 minus 4 into the original length is 500 mm. So delta L is 7.162 e to the power of 4 into 500 gives us we got the same value 0.358. See, I have shown you the two methods to determine the strain and the change in length. So this is how we are going to solve the problems in the first module. We will use the basic equations and we will determine the unknowns. Okay, let us see the next problem. The problem is given to us like a specimen of steel 25 mm diameter with a gauge length of 200 mm is subjected to destruction. A specimen of steel 25 mm diameter with a gauge length of 200 mm is subjected for destruction in a tensile test. Full stop. The extension of the bar is 0.16 mm at a load of 80 kilonewton. The extension of a bar is 0.16 mm at a load of 80 kilonewton, comma, the load at elastic limit is 160 kilonewton. The load at elastic limit is 160 kilonewton, comma, the maximum load acting on the specimen is 180 kilonewton, full stop. The extension of the member at fracture is 56 mm and the diameter of the neck or the neck diameter is 18 mm, full stop. I will repeat the problem. A specimen of steel 25 mm diameter and with a gauge length of 200 mm is subjected to destruction in tension test, shows an elongation of 0.16 mm at a load of 80 kilonewton, comma, the load at elastic limit is 160 kilonewton and the maximum load acting on a member is 180 kilonewton, full stop. The extension at fracture is 56 mm and diameter of the neck is 18 mm, full stop. Determine stress at elastic limit, Young's modulus, reduction in cross-sectional area, percentage elongation and ultimate stress. So, this is a problem given to us and this is a very important problem which can be expected for 10 to 12 marks. So, let us start. So, first, as I said in the previous problem, the first duty is to identify the given data and designate them with the known notations. So, by reading the first line of the problem, a specimen of steel 25 mm diameter, I give that as initial diameter, D is the notation for diameter and suffix I represents initial diameter and it is 25 mm. Next, gauge length, it is the initial length of the specimen before the test and it is under our experimental consideration. So, length is given by L, I designates it is an initial length and the length given to us is 200 mm. Extension or elongation is generally denoted with delta and the value given to us is 0.16 millimeters and the load acting at the corresponding time is 80 kilonewton. For the load we have given the letter as P equals 80 kilonewton. Then they have specified load at elastic limit. So, load is given by P, elastic I have designated that with a suffix EL, EL stands for elastic limit, load at elastic limit is 160 kilonewton. So, the maximum load is P is the load, maximum load 180 kilonewton. Then the final extension or extension at the fracture, it is the phase where the specimen has broken into two halves. At that particular time, the final extension is 56 mm and the diameter at that particular time, that is the final diameter or the next diameter is 18 mm. These are the data given in the problem. And now let us look into the unknowns that they have asked us to find. So, they have asked to find stress at elastic limit, Young's modulus, percentage reduction in area, percentage elongation and the ultimate stress. So, these are the unknowns and these are the data given in the problem. So, to start with, as we have seen, the basic definition of stress goes like force by area. Again observe, in the problem they have not specified the area but they have given the initial diameter and the diameter at the neck. Based on these two diameters, let us find out the initial area and the final area. And the form expression or the formula for the cross-sectional area of circular member is pi d square by 4. Since it is initial, I will take initial diameter, that is di. Pi into the initial diameter 25 square divided by 4. Pi 25 square by 4. If we solve this, we get this value as 490.87 millimeter square. So, this is the initial area. So, let us find the final area. AF pi df square divided by 4. Pi final area, the diameter is 18 square divided by 4. So, on solving this in calculator, we get this value as 254.47 millimeter square. 254.47 millimeter square. So, this is the initial prerequisite for solving our problem. Let us start with the first case. So, the first one is elastic stress, stress at elastic limit or elastic stress. So, we will denote that with sigma E suffix L. So what is stress? Force by area. So if it is stress at elastic limit, so what should be the load I should consider? It is the load at elastic limit. And what area I should consider? It should be the initial area. Initial area. So do we know the load at elastic limit? Yes, it is given as 160 kilonewton, and we found the initial area as 490.87. So on solving this, we get this value, the stress at elastic limit, as 325.5 Newton per mm square. So stress at elastic limit is found. Sigma EL equals 325 Newton per millimeter square. It is a straightforward expression of our basic definition of stress, P by A, and since they have asked stress at elastic limit, we have used a load at elastic limit and the initial cross-sectional area. Now let us find the Young's modulus or modulus of elasticity. Young's modulus, that is E. So to find the Young's modulus, we should remember some very important law that we have seen in our module, that is Hooke's law. What does that Hooke's law says? Hooke's law says stress is directly proportional to strain, and very important phrase in that law is within the elastic limit. Within the elastic limit means everything should happen well within 160 kilonewton. So from Hooke's law we know stress equals Young's modulus into the strain. So our duty is to determine what is the value of Young's modulus or modulus of elasticity. I can rearrange this equation to get the value of E, that is sigma by epsilon. Now a problem arises, what should be the value of this sigma and what should be the value of this epsilon, that is what should be the value of stress and what should be the value of strain, whether it should be the stress at elastic limit or it should be the strain at elastic limit. Remember, Hooke's law holds good within the elastic limit, at least well within 160 kilonewton. So we have some elongation and the load within the elastic limit, that is load within the elastic limit given in our problem is 80 kilonewton, and the elongation within the elastic limit that is given as 0.16 millimeter. So we will make use of these two to find the stress and the strain. So stress P by initial area. So based on this, we have a P as 80 kilonewton. Initial area, we found the initial area as 490.87. So we can find the value of sigma, that is 80 by 80 E3 divided by 490.87. So we get it as 162.97 millimeter square. This is the stress within the elastic limit, and sigma EL is the stress at elastic limit. So we found the numerator. Let us find the strain within the elastic limit. So we know strain is given by delta L by L. So strain elongation within the elastic limit given to us is 0.16 mm and the gauge length is 200 mm. So if you solve 0.16 divided by 200, we get it as 0.8 into 10 power minus 3. Remember, the strain is a dimensionless quantity. Now we know both the numerator as well as the denominator. Let us find the Young's modulus. Stress 162.97 divided by the strain 0.8 into 10 power minus 3. So we saw on solving this 162.97 divided by 0.8 into 10 power minus 3, we get the Young's modulus as 203.71 into 10 power 3 Newton per mm square. 203.71 into 10 power 3 Newton per mm square. So, we found the Young's modulus or modulus of elasticity. Let us go to the next unknown, that is percentage reduction. Percentage reduction in area. Percentage reduction in area. This is given by initial area minus the final area divided by the initial area into 100. So, we know the initial area. What is the initial area? So, for 490.87 minus the final area 254.47 divided by 490.87, entire thing multiplied by 100. So, the percentage reduction in area, we get it as 48.16. Percentage reduction in area is obtained as 48.16. So, we have found the third unknown. So, we know we have found stress at elastic limit, Young's modulus and percentage reduction in cross sectional area. Now, let us move on to determine what is the percentage elongation. So, the percentage elongation is given by final length minus initial length divided by initial length into 100. But observe, in the problem they have given extension, total extension of the bar. What is this total extension? It is nothing but final length minus the initial length. Total extension is nothing but final length minus the initial length. So, we know that final length minus initial length as 56 mm. What is the initial length? So, we know that value as 200 mm into 100. So, the percentage elongation is obtained as 28%. 28%. So, we found the stress at elastic limit, Young's modulus, percentage reduction in area, percentage elongation. Let us find the last unknown, that is the ultimate stress. What is ultimate stress? What is ultimate stress? It is the stress at maximum load. It is a stress acting on a member for the maximum load. So, please observe the data that is in the problem which gives you the maximum load. And they have specified the maximum load acting on the member as 180 kilonewton. Maximum load acting on the member is 180 kilonewton. Therefore, we can find sigma ultimate, that is ultimate stress, equals maximum load divided by initial cross sectional area. So, the maximum load is 180 kilonewton. The cross sectional area initial is 490.87. Therefore, the ultimate stress is obtained as 366.65 Newton per mm square. 366.65 Newton per mm square. So, please carefully observe here. So, the unknowns given to us is elastic stress, Young's modulus, percentage reduction in area, percentage elongation and the ultimate stress. So, as I said, this problem will be asked for 10 marks. Each unknown carries 2 marks, and the formulas or the expressions that we have used is the basic equations of stress and strain, that is all. So, we know we have found out the initial area and the final area. Then we determine the elastic stress by making use of the load at elastic limit and the initial cross sectional area. Then we found the modulus of elasticity or the Young's modulus by applying the Hooke's law, which states stress is proportional to strain within the elastic limit. So we identified the data given within the elastic limit, and based on that we found the modulus of elasticity as 203.7 into 10 power 3 Newton per millimeter square. Then we found the percentage reduction in area by making use of initial and final areas, found the value as 48.16%, and percentage elongation. In the problem they have specified the final extension, total extension is 56 mm. Total extension mean in the sense final length minus the initial length, which value is given 56 mm and the initial length was 200. The elongation percentage is 28%. Then the ultimate stress. We identified the term which gives us the maximum load acting on the specimen, that is 180 kilonewton, and it is acting on the area of 490.87 millimeter square. So based on that we have obtained even the ultimate stress. So this problem is very important for in the exam, because which carries 10 marks. Along with this problem we may expect one of the derivation, either the tapering rod or the tapering circular rod or tapering rectangular bar. So which we will fetch 20 marks completely for us. So we will see the next problem. Okay, let us move on to the next problem, that is problem 3, where the problem goes like this. A specimen of steel shown in the figure is subjected to tension test in UTM. A specimen shown in figure is subjected to tension test in UTM, full stop. It is observed that at a load of 40 kilonewton, the extension of the bar is 0.285 mm. At a load of 40 kilonewton, the extension of a bar is 0.285 millimeters, full stop. Determine the Young's modulus of the specimen. This is the problem given to us. In the problem, even they specify the diagram. The data mentioned on the diagram will be given to us. So let us write down the data given to us. So the data specified in the statement is, the specimen given to us is subjected to tension test. The load acting on the member is 40 kilonewton. The extension of the bar is 0.285 mm. So it's, when we see the diagram, it clearly shows it is not of uniform cross section. It is a member with different cross section or stepped cross sections. We have 3 sections here. One is, I have denoted that with section 1 having a diameter of 25 mm and having a length of 160 mm. Section 2 having a diameter of 20 mm and a length of 240 mm. Section 3 having a diameter of 25 mm and a length of 160 mm. And they have asked us to find Young's modulus of the specimen. As we have done in the previous problem, our first duty is to write down the given data. Once we have identified the data mentioned in the problem, the next is we should check whether the cross-sectional areas are given or the diameters are given. If the diameters are given, find out the cross-sectional areas. Cross-sectional area, that is A1 pi d1 square divided by 4 pi d1 25 mm square by 4. On solving this, we get this as 490.87 millimeter square. Observe that section 1 and section 3 have got the same diameter. So what I can do? I can say A1 equal to A3 since the diameters are same. Then A2 pi d2 square divided by 4 pi into 20 square divided by 4. On solving this, we get 314.16 millimeter square. 314.16 millimeter square. So we found the area of first section, second section as well as the third section. So we have done with this. Now how to go for the Young's modulus? So we have three different sections. In our theory classes, we have seen an expression for change in length of the bar if it is having uniform cross section. For change in length of the bar, for uniform section, we had an expression of delta L equals PL by AE if the cross section is uniform. If it is a stepped section, we have seen an expression delta L equals P1 L1 P L1 divided by A1 E1 plus P L2 divided by A2 E2 plus P L3 divided by A3 E3 and continues. When we have different cross-sectional areas, different lengths and even different material. But luckily in this problem we have given with only one material. So in the place of E1 we can just have E. So this expression can also be written as delta L equals delta L1 plus delta L2 plus delta L3. That is elongation of the first section plus second plus third gives us the total elongation. The total elongation is already mentioned in the problem. That's value is 0.285 mm. 0.285 mm. So let us start solving this. So I will make use of the first expression delta total elongation P by E. Since the load acting on the member and the modulus of elasticity is same, I will take this common. So we are left out with L1 by A1 plus L2 by A2 plus L3 by A3. Let us substitute. So the required term in this equation is Young's modulus. Now only I can shift this Young's modulus to the LHS and send the delta T, that is total elongation, to the RHS. So E becomes P by delta T L1 by A1 plus L2 by A2 plus L3 by A3. L1 by A1 plus L2 by A2 plus L3 by A3. So load acting on the member is 40 kilonewton. Total extension observed is 0.285 mm. What is the length of the first section? 160 mm. What is the initial area of the first section? 490.87. Plus what is the length of the second second section? 240. The area 314.16 plus length of the third section 160. Area 490.87. Solve this for the Young's modulus. So Young's modulus, on solving this using the calculator, we get this as 198.72 into 10 power 3 Newton per square. 198.72 into 10 power 3 Newton per mm square, and it can also be said as 198.72 kilonewton per mm square. So this is how we find the Young's modulus when the load and extension of a member is given. So we will see in future, we will see the problems when the Young's modulus is specified, load is given, and they will ask us to find the total extension of the bar. So as we have done the first problem. Okay, let us move on to the next problem. Where we have been given with a stepped bar with along with stepped we have an tapering section also. So the problem statement goes like this. A stepped bar as shown in the figure is subjected to an external load of P equals 40 kilonewton. P equals 40 kilonewton. Full stop. Determine the total extension of the bar. Determine total extension of the bar. Full stop. Take Young's modulus of steel as 200 gigapascal, Young's modulus of aluminium as 70 gigapascal, Young's modulus of copper as 100 gigapascal. So this is a problem where we need to determine the change in length or total extension of the bar. I will repeat the problem once again. A stepped bar as shown in the figure is subjected to an external load of 40 kilonewton, full stop. Determine the total elongation of the bar, full stop. Take Young's modulus of steel as 200 gigapascal, Young's modulus of aluminum as 70 gigapascal, Young's modulus of copper as 100 gigapascal. So as I said, we should start the problem by identifying the given datas. So the datas, by reading the first line of the problem, we can identify the member is subjected to an external loading of 40 kilonewton. And we have three different materials: steel, aluminum and copper. Let us note down the Young's modulus of steel, which is 200 gigapascal, Young's modulus of aluminum 70 gigapascal, Young's modulus of copper as 100 gigapascal. And the diagram figure is given to us. So in the figure, by looking into the figure, we can write down the diameter of the steel. That is, I will denote that with ds as 20 mm, and the corresponding length ls, I will write that as 300 mm. Then the diameter of the copper is given as 50 mm. The length of copper is 200 mm. So in between we have an aluminum section which is tapered. So the length of aluminum section is 200 mm. By looking into the diagram, we can say the aluminum section is a tapering circular rod, because at the smaller end we have a 20 mm diameter, at the larger end we have a 50 mm diameter. So we have three different sections and three different materials. Our duty is to find total extension or total elongation of the bar given to us. So as we have done in the previous problem, we will calculate the elongation of steel, elongation of aluminum, elongation of the copper individually. Then we will add all together, since this is subjected to tension. Since it is subjected to tension, there will be elongation, there will be increase in length. So we are going to add the individual elongations to get the total elongation. So first section, let us call elongation of the steel. The steel section is a uniform section having a length of ls, area of as and Young's modulus of es. Area of as and an Young's modulus of es. Let us find the area of steel. Pi ds square divided by 4. Pi into 20 square by 4. We get 314.16 mm square. Let us find the area of copper even now. Pi dc square divided by 4. Pi into 50 square divided by 4. We get a value 1963.56 millimeter square. So we have found the area of steel as well as copper. Now one different thing you should observe, the Young's modulus are given in terms of gigapascal. And while solving the problem, we will convert all the gigapascals or pascals or newtons, millimeters, everything we will give a conversion in terms of, keep it in terms of millimeter square. Let us see how to convert this gigapascal into millimeter square, Newton per millimeter square. So I will show you the example for steel. Steel is given as 200 gigapascal. Giga means 10 power 9. Pascal means Newton per meter square. 200 into 10 power 9 Newton. So 1 meter is 1000 millimeters. And we found it as meter square. So 1000 millimeter is nothing but 1 meter. 200 into 10 power 9 divided by 1000 square, we will get that as 10 power 6. So once we cancel, we get the Young's modulus of steel as 200 into 10 power 3 Newton per millimeter square. So that means to say gigapascal can directly be written as 10 power 3 Newton per millimeter square. So this is how we will convert gigapascals to our simplest unit, that is millimeters or millimeter square. So let us proceed to solve our problem. So delta S, that is elongation extension of steel. So the PS 40 kilonewton. The length of steel is 300 mm. 300 mm. Then we have area of steel as 314.16. Young's modulus of steel. I have converted the gigapascals to Newton per millimeter square. Carefully observe that. So it will be 200 into 10 power 3 Newton per millimeter square. So the extension of steel, elongation of the steel, after calculation we get that as 0.1909 millimeters. We get the elongation of steel as 0.1909 millimeters. Let us find the elongation of copper also. So copper, it will be PCU LC divided by AC into EC. So PC, the load 40 into 10 power 3, the length of copper 200 mm, area of copper we found that as 1963.56 into the Young's modulus of copper. So 700 gigapascal can be written as 100 into 10 power 3 Newton per mm square. So delta C, if we get it as 0.0407 mm. 0.0407 millimeters. So we have determined the extension of uniform sections. Let us see what is the elongation of the tapering section. The tapering section is for aluminium, and please remember, just look into the list of formulas we have written. For a tapering circular rod, the expression for elongation is 4p L divided by pi E d1 d2. This is a general expression what we have derived. Let us modify this expression according to our data what we have written and the notations. So the tapering section is for aluminium. So I will write AL into the length of the aluminium, then pi Young's modulus of aluminium into the diameter. The first diameter, the smaller diameter is steel's diameter of the steel, into the larger diameter is diameter of the copper. Now on substitution, delta AL equals 4 into 40 into 10 power 3 into the length 200 divided by pi. Remember the Young's modulus of aluminium as 70 gigapascal, which can be written as 70 into 10 power 3. Diameter of steel is 20 mm, diameter of copper is 50 mm. So on substitution and on calculation, we get delta AL as 0.1455 mm. Observe, we have found the extension of steel, extension of copper, as well as extension of aluminium. Now since we have got the three extensions, let us find the total extension delta T. As I said, since it is subjected to tensile load, it will be increasing in length. Therefore, we are going to do the addition of all the three sections, that is elongation of the steel plus elongation of the aluminium plus elongation of copper. So the steel elongation of steel is 0.1909, elongation of aluminium is 0.1455 plus elongation of copper as 0.0407. So the total elongation, we get it as 0.3771 millimeters. 0.3771 millimeters. That means to say, for a load of 40 kilonewton, this cross section which is having both uniform as well as taper will show a total extension of 0.37 millimeters, 0.37 millimeters. So, in the further classes we will see the problems where the member will be subjected to different loads, like with the different combinations of the section and different loads.